So till now we have discussed about blinking an LED, and we have discussed different approaches by which we can blink the LED. And just for time sake or for just name sake, I'm going to show you what we have done in the last two lectures. First thing is to find the base address of the port in which you want to make the LED on or off. For that, you have to check the data sheet or you have to find the schematic. Okay. Now, to enable any enable any port, we have to first provide clocks to that port. We call it clock getting, and we have seen which register is used for clock getting. If you can tell me which register was used for clock getting.
RCGC GPIO.
Right. So RCGC GPIO. Remember. So here we are actually enabling the clock of the GPIO. Similarly, there are many peripherals like timer. Okay. You have timers are there. You have ADC, DACs are there. So there are so many other devices or peripherals which are there. In future, if you need to use any of those features, you will have to first check whether you have to provide the clock to that particular peripheral or not. Okay. For that, you can go through the data sheet again, and if needed, you can check the bus architecture, which bus is connected to which of the clocks or which of the peripherals. Now, since we were using port F, because inbuilt there are three LEDs which are inbuilt on the board itself, the red, green and blue LEDs, and we also saw the data sheet which pins are connected to these three LEDs. We have gone through that data sheet also, and therefore practice, the more you practice, the faster you can reach to these registers and these LED pins. Okay. So it's not that you just see the presentation. Please, at the same time, practice how to open the data sheet, go through the data sheet as soon as possible or as fast as possible. Now, then you have the direction register, which will tell whether the pins that you are focusing, for example, the pins for the LED, are going to be output or input. Because we are using the LEDs, LED is an output device. Okay. So we will configure the bits 1, 2, and 3 as an output port. Okay. So port F's 0, then after that 1, 2, 3. So D1, D2, and D3. You have to configure them as an output. Okay. Then we make the LEDs on or off by using this particular register, data register, so that we can change whatever we want to change on that particular pin. Okay. So to reach to the final address, of course, we also know that to reach to the final address or the complete address, we need to know the base address and then the offsets. Base address means, for example, when we are saying the base address, then we are interested in GPIO port F. Okay, so port F's base address we should know, and then of course each port will have multiple registers like the one which are shown above. Okay, direction register, then you have data register, digital enable register, and similarly interrupts and all other features are there. So there are so many registers which are there, okay, in single port, and we have to reach to that particular offset. Offset means here, for example, dir register is one of the offset register, then data register is an offset register, then you have digital enable, which is again the offset. Okay, so we have to know the complete address, and then in that register we have to change the values. We know that part. So briefly, please open the data sheet and cross check these things, okay, side by side, and keep your IAR software open, so that when I am writing a code or when we are modifying a code, you can parallelly change or modify the code. Okay, so that you can even practice how to create a project, how to select the microcontroller, then how to select whether you are going for a simulator or you are going for the microcontroller board and all. Okay, so the base address of GPIO port F is 400 to 5000. This is the base address using which bus? Can you tell me the bus which is using 4000 to 5000 address? Which bus we are talking about?
APB.
APB. Okay. So basically we are talking about APB. There is another bus, AHB. You can use that one also. In this class, you can try to go for that also. Okay. So we know that the GPIO port F start address or base address is 4000 to 5000. Okay, this I have shown you that when the board is just connected and if you don't provide the clock, or when the clock is not enabled, the ports have this minus sign in the port. Okay, so in the registers, so this I have shown you. Okay, so we need to provide the clock getting done. Okay, this we know that we have to reach to the fifth pin or the fifth bit of RCGC GPIO. Fifth bit because we are talking about GPIO port F. Okay, so please open the data sheet parallelly. Okay, if you have any doubt, you can open the data sheet. So in this you can see GPIO, RCGC GPIO. So this is clock gating, and you come down here, you can see there are 6 registers which are allowed for our purpose or any clock providing for the particular port. Why 6? Because there are 6 ports. So 0, 1, 2, 3, 4, 5, and remember these are all read write, read write, read write. So read write means you can read or write these bits. Okay, so pin number 5 or bit number 5 here. Okay, mm, just a second. Okay, here bit number 5, okay, is basically for GPIO port F run mode clock getting, and we have discussed this part. Similarly, for pin number 4, if you are interested in port E, you can go for bit number 4. Okay, now this was done. Sorry. Now RCGC GPIO has a base address of 4000 FE000, and we are going for offset of 608. So the complete address to reach to the port F's RCGC GPIO is 400 FE608. Okay. Then to enable the fifth bit, because you can write this whole number, okay, because this is 0000 32-bit register is there. Okay, this particular register 4000 F E608 is a 32-bit register, so this 32 bit will look like this. Okay, and at the end you have 00100000. So this is D0, D1, D2, D3, D4, D5. Why? D5 is the bit for port F. Okay, so therefore we have to enable that bit. So you can enter, instead of writing this whole number, you can even write 0x20. Okay, and that will enable the clock on the port F. Now, after the clock is enabled, we have to tell which pins are we focused on, and depending on those pins we have to tell whether those pins will be acting as an output or input. For that we will use the direction register. Okay, and the direction register is GPIO dir. Clear. And the offset for that register is 400. So this is our base register. 4002 5000 was the base address. So this particular 5 digits are common for all the registers in the port F, and 400 is our offset to reach to the dir. And in the dir we have to tell that in the dir, for example, this is the port F's base address 4000 to 5000. Okay, and then the dir, sorry, this is data register, my mistake. I have not the register is wrong here. Let me just open the correct register, no issues. E, no, no. Okay, you can open the data sheet from your end. Okay, so wait a second. Okay, you can directly go to GPIO dir and it is taking time to search that. Okay, this one is the register. So here we can see the base address is port F. So base address of port F is 4000 to 5000 and offset is 400. And with that, you will reach to this particular register, GPIO direction register. And then you will have to tell, because here we are using 8 pins. Why? Because each port has got 8 pins. So we have to tell which pins we are interested in and which pins are going to become input or output. Okay. So from that, you can see here, we have to talk about these 3 pins, because these 3 pins are going to be used for our project, because LEDs are connected to these 3 pins. Rest, fourth pin, this pin and this pin are switches. Okay, so we have to talk about these 3 pins, and then we can see from here GPIO direction register 0 corresponds to input. That means if you are using these pins as an input, you will have to write 0 on that. If you are interested to make them output, you have to put 1 on that. Okay, done. So we will go to that particular port and make it output pins. Then after that, for to make the output pins, we are entering 0E. Why? Because 0, 0, 0, 0, 0, sorry, 1, 1, 1, 0. Okay, so this is D0, 1, 2, 3, and 4. So these 3 bits are becoming output. Okay, so we are connecting LEDs to these 3 pins. Therefore, E is representing 1, 1, 1, 0. Okay, E is 1, 1, 1, 0, and these 3 bits are output. Therefore, done. We are telling that these 3 pins are going to work as an output. Then after that, we have to tell the system that these 3 pins should work as a digital input or output. So for that, the offset is 51. So 40025 51C is our offset. Go to that register and tell that these 3 pins are going to become digital input output. So therefore again these 3 bits, that is 0, 0, 0, 0, 1, 1, 1, 0, these 3 are digitally going to work as a digital input output, because they can either be 0 or 1. Instead of that, if you are interested in making them analog input output or PWM, then you have to make it 0. Okay. Now after that, we just have to go to the data register and then write the values corresponding to the LEDs. For example, 02, so 0000 so this is red LED, right? 04, so 0000 this is our blue register, sorry, blue LED. And then 1000 this is our green LED. Okay, so depending on your choice, whichever LED you want to make one, or whichever LED you want to glow, you can pass 02 for red LED, 04 for blue LED, 08 for green LED. So this is what the whole cycle which is used to write the program. Okay, and we also checked the code. So this is all just summarized in a very short period. Okay, so this was the program which we used, and instead of using these particular commands which are focusing on the address and then dereferencing the pointers to that address and entering the values to that particular address, we can even use header files. We have discussed about that in the last class, and I have shared the header file also. Okay, so this was all about the story of making an LED high or low. And also, yeah, we discussed about why we use 400253FC. 3FC is used because this particular 9 to 2 are used to make the port F's, okay, output data register. Okay, we can then change the values. So this is another approach. Leave it. Now, can you change the same code for making the LEDs on or off using AHB? Now it is your job. Tell me the base address of GPIO port F's AHB using AHB. Base address of port F using AHB. Continue. Hello. Can you tell me the base address
So it
of
is
port F?
4005 D triple zero.
4005
D triple zero for
8
D D
D.
D
Okay. Let me check. Okay, okay. Please,
uh,
everyone, please.
for port F.
Wait. Port F.
Yes, it is for port F.
Okay. D00H.
Yes,
So I hope everyone is getting this address. If not, we can just cross check it here. Okay. So high speed bus. No, first you have to go to clock getting GPIO high performance bus. D00. Ah, sorry, the port Fs, right. You are going for this one. You're talking about this one, right? This port F
yes, sir.
D00. Okay. Now, first we have to reach to this particular address that is decoded 4005 D000. What about the clock? Because how to enable the clock for this particular bus? What is the address for that particular clock? Check. High speed bus clock. Okay. So you can go to GPIO HBCTL because this is high performance bus clock CTL. Okay. And you can read from here. This register controls which internal bus is to be used across the GPIO port. When bit is clear, the GPIO port is accessed using legacy or APB. Okay. When bit is set, when we make it 1, the corresponding port is accessed via AHB. So you have to reach to this particular GPIO high performance bus control. Okay. So for that, the address is 4000F E000 and the offset is 06C. So the complete address is 400F E06C. Please cross check it. Okay. Register 9 of the this. So GPIO HBCTL. So in the reference, you can go here and just type GPIO HBCTL. Okay. And that will take you to the bus. First of all, remember, I told you whichever port or whichever peripheral you want to access, there are two options. One is using APB, normal bus, and the second is using high performance bus. And here we are interested in GPIO, high performance bus. So this one, okay, you have to reach to this address. Done. To make the clock active on the port F using high performance bus. Now coming to the, we have the now we know that we have to go to this particular register. Okay, let me just open the IAR along with this. Okay, IAR. We will close this particular project, close workspace, and we will open the previous project which was there. Okay, so we were talking about LEDs, blinking LEDs, toggle LED. Let me check if I'm using the header file or not. No, in this we don't have the header file. Anyway, let us go through the project, and I believe in the project we have the header file. Anyway, now in this GPIO register, again we can see the port F is at pin number 5. Okay, so bit number 5 will make the port F activated using AHB. So if I make this bit 1, then we'll be using AHB. If this bit is 0, then we'll be using APB. So because we are using AHB, we'll make this particular bit 1. Okay. And this, don't worry about this particular register right now. This is taken from the header file. We will come to that. Now, this command, I believe you remember what is this command doing here. This command is used for which purpose?
Side
For
shifting.
putting 1 at 5th position.
Left shifting. Okay, bitwise I can write it more precisely. Bitwise left shifting to left shifting 1, okay, to 5th position. Okay, so we are interested in introducing 1 in the 5th bit position here. Okay, therefore we can use this particular command, that 1U means 1. Okay, 1, only 1, and it is shifted by 5 positions, so you will reach here. Okay, so to introduce 1 in this particular bit position, we are using this command. So bitwise left shifting command. Okay, and we will come to this register. How to find this register, we can check that through the header file, don't worry. Now let us Rest everything will be same. We'll have to make the port F's direction, digital enable, and data. That's all. Only thing that we have changed is instead of using normal GPIO register, we are using high performance bus. Okay. So this command, you remember that to make the LED, red LED one, we have to come to the first position of the GPIO port F. Okay. And for example, I will just pick it like this. Here, this is 0000. Okay. 0010. Okay. So this is the first position because LED red is connected to the first bit position of port F. Okay, done. So we this is used to make the red LED high, and then okay, let me just go this. This one instead of red we have blue LED, and here we are moving to the second position. And here we are moving to the third position, and that will make the green LED on. So this is the simplest way to approach to different bit positions. So we know that to reach to the red LED, we have to make D1 high. To reach to the blue LED, we have to make D2 high. And to reach to the, this one will be 0 and 1. Okay. Okay. Mistake again. 1, 0. Okay. So this is the D3 position. Done. So this is how we can make the three LEDs on. So we are using macros to define LED red, LED blue, LED green. This was done in the past. Now let us check the header file. I have shared it in the classroom. So I will just open the header file. And to keep the header file side by side, you can go to Windows, okay, and move the tab to new vertical editor window. That's all. So now you have two views. Simultaneously, you can see your main code as well as the next file, which is the header file. Okay. And in this, you can go to this file, Control F, and you can just go to GPIO HB CTL. So this will take you to the header file, which is containing all the list of registers which are there in the microcontroller, and we are interested in GPIO HBCTL register, and the address is 400FE06C. You can see from here also, yeah, 400FE06C. This is the address for the HBCTL. Okay, so you can just copy this particular register and paste it here, and then you are moving to the fifth position, making it high, that is making the clock for port F high. So you are enabling the clock on that particular port. Okay, then after that GPIO register, you don't have to enable this particular, I think this is done. Port F is done. Okay, and then you are using AHB dir. So because you are using everything in the AHB, you can just go here, Control F, AHB. This is all related to the, let me just open the header file in separate window. Let just a second. Go up, header files. Okay, pair registers. Here we have. And I can go to AHB. Okay, here you can see port AHB. We have to go to the port FAHB. So Control F and port FAHB here. port F's AHB. So all the registers which are connected to high speed bus in port F. Okay, so these are all the registers. So here you have the DIR register, you have the data register, and then DEN, digital enable register. So you need these three registers right now. Okay, so you can note these, take these registers, copy them, and change the previous program where you were using normal port F bus, okay, APB. Instead of that, you are using AHB. Therefore, these are the three register: digital enable, DIR, and data register. Done. Okay, and you can just change those registers here, and rest of the program is almost the same. You are not changing anything else. So instead of APB or normal GPIO port F, you are using high speed data bus. That's all. So you can see here, this is AHB, and you can go to here, control F, port F. This is AHB. Okay, sorry. Done. These are all the ports detail. In the past, we used normal bus from port C, port D, port UART, port F is here. Where is port F? Port E, port F. So these are the registers which don't have the access to AHB. These are normal registers. So in the past, we use these registers. Okay. Now, if you need AHB, you can just go here, port F space AHB. Okay, and you can come to this block of registers which are there for the high speed bus. Change the values for those particular registers, copy paste the registers, and done. Okay, and this is the program which is generated in the previous lecture. Instead of using normal port F, we are using AHB. Okay, you just can change these registers and done. Nothing else is changed here. First is we are providing the clock using high speed clock bus, and then we are using high speed bus for the GPIOs, DIR, digital enable, and data. Done. Rest of the while loop and everything is same. Any
Sir,
doubt? Mhm.
so when we are using the HB port itself, then why are we using that HCBTL? Why are we enabling that?
Which one?
So the first one, this
This
line
one.
number 11.
This one.
Yes, sir. Yes,
Because
sir.
we have to provide the clock, you the high speed bus clock, na? So we have to go to the high speed bus clock to enable that particular bus. For example, before you used, wait a second,
RCGCGPIO.
your voice is cracking.
So before we used RCGCGPIO, so this is the alternate to that for
Before,
EHP.
for the AHB, wait a second. Before you use GPIO bits for, let me show you the GPIO port. Okay. So system control, register map, and before you have used RCGC GPIO. Okay, this one was the, sorry, this one was the offset 608, right? This was the offset for RCGC GPIO to provide the clock for port F, right?
Yes, sir.
Now this time you are using high speed bus clock. Okay, and for that, if you have any confusion, go to the architecture, let me just close this and go to the architecture of the I think you have not attended that particular class. Wait,
No,
close.
sir, I've understood. I've understood.
Okay, just a second, let me show, because some of the students still may have that doubt. If I have the here, no, bus architecture. Wait a second. Architectural overview, block diagram. Let me just check. No, this one was not that. Bus architecture. No, not this one. Block diagram. No, functional diagram. No. Where was the bus? Bus matrix. Let me check. Or otherwise I will have to go to that particular slide where I was showing you the bus diagram. This one. Here. You can see here all the ports, okay? All the ports can access both AHB and APB. Let us check the ports. So here you have the GPIOs. I hope you can see here GPIOs, 43 GPIO pins. And these GPIOs can access both the buses. The high performance bus, AHB, you can see the small arrow here, bidirectional small arrow. So that can use AHB. At the same time, there is a long arrow, this one, which shows it is also connected to advanced peripheral bus. So to enable this bus, you will have to use RCGC GPIO. Okay. Enable this bus. To enable this bus, you will have to use HBCTL, this one, high speed bus. Okay. Where was that? HBCTL. Okay. Clear? GPIO, HBCTL. You have to go to this particular register to enable that particular high speed bus. Okay, I believe it is clear now. Okay, so before you were using RCGC GPIO, which was enabling this advanced peripheral bus. Now, if you need advanced high performance bus or AHB, you will have to go to this particular bus, which is HBCTL. Okay. So you have to keep an eye on the bus architecture to access those registers. Rest of the code is same. So there is nothing new in this thing. So you can just change the bus. Then you have to change the registers which are connected to those particular high speed bus. Okay. And of course, if you don't recall those or if you cannot remember those particular registers, you just go to GPIO here. Okay. And in this, you can check the register map. And there, these registers are always same, 402 5000 and 405 D000. This will be the this will remain always same because these are the base registers. Rest offsets will be changing. Okay. Only the offsets will be changing. These offsets are common for both 4002 5000 and 4005 D000. And that you can cross check from this particular address also. For example, let us take an example. GPIO port of AHB DIR. DIR you can see here, okay, AHB. So 4005 D400. D400, okay. So D000 is common and 400 is common for whether you use AHB or APB. Okay, because these are the same common offset. Only thing you are changing is the base address or the bus which you want to use, AHB or APB. Clear? Anyone having any doubt in this particular whole structure? Anyone having any doubt? What we are doing and how we are reaching to those particular addresses and why all these things are required? Okay, let me briefly tell you what we are doing here. Every peripheral. Okay, so there are many peripherals in the microcontroller. Out of those peripherals, you have GPIO also. Okay, so you can also have ADC, DAC, and so on. Okay, we are focused on right now on GPIO, and GPIO is connected via two buses. Okay, so two buses are there. One is APB, and the other one is AHB. AHB is fast. Okay, it takes only one clock to complete that assigned job, and here this one is a bit slow because this is legacy or the old bus. Okay, technology. Now each one has its own base address. So 4002 D triple zero, and here you have 4000 to 5000. Okay, and then after this these buses have been enabled, and then you have all different offset registers which are there, and these offsets are always same. You can check from there that this is the offset for dir, digital enable, or data. Okay, so you can check all these registers, these are always same. Okay, the offset for these registers are always same. So what you are doing, first of all, you are enabling the clock. So you are enabling the clock for this particular um, bus. Okay, and then after that you are reaching to these registers. Okay, and each register has its own job, like whether you want to make the pin input or output, whether you want to make it digitally enabled. Okay, digitally enabled, or you want to make it analog, and so on. And the data means whether you want to make it high or low, or when you want to write or read something. Okay, so when you want to write something, you can make it high or low. So this is what the story is, and for that we can use two different or three different approaches. One is using the registers directly. For that you can use pointers, and these registers again are arranged in consecutive memory addresses, consecutive memory addresses. Okay, so you will always find that they have addresses which are linked in the 32-bit alignment system. Therefore 0 4 8 C, again 0 4 8 C. The last address or the last bit or last digit will be always same, because this is 32-bit aligned, 32-bit aligned addresses. Okay, so this is always common. So now we can correlate this concept with, because these are aligned in consecutive memory addresses. So consecutive memory addresses concept is coming from your um, arrays. Okay, so if you know the array, okay, you can access the index of any array, and then using pointers and arrays you can change the value of any particular register. So we are taking the help of C and the concept of pointers. Till now we have talked more about the pointers and arrays, and then manipulating the values using pointers dereferencing and all done. So this is all about the summary of the programming using embedded C and writing programs for your microcontroller. Anyone having any doubt till this part, what we are doing and how we are reaching to this particular memory and all? Of course, for this whole thing, we are using the data sheet. Anyone having any doubt or difficulty? If not, then we can move ahead. Okay. Please, I have provided you the header file. Do open the header file and write the program using the header file. Okay. This we have done. Okay. Now coming to, because whatever we have studied in the C, I am now correlating all those stuffs in programming the microcontroller. Okay. Of course, in C we have discussed about functions and stack, and now we are going to check how we can use functions to make better programs. Of course, we can write programs in this kind of way. Okay, so further, can we improve the way to write the program? Because this is working, so there is no harm in that. We can use this approach. This is working. Okay, you can take the help of header file, go to the particular register, enter the value using bit level shifting. Done. And you can use bitwise ANDing and ORing. This is bitwise ORing to make a particular bit high. Bitwise ANDing will be used when we want to make a particular bit 0. Okay, here we have not used bitwise ANDing till this part. Okay, done. So let us now take the help of functions to further improve the quality of writing any program. Okay, so functions and stacks. So whenever we talk about functions, we also talk about the stacks, how the stacks are basically managed and manipulated. Okay, when we write any program or when we run any program. So stack, we know the concept of stack from 8085. Stacks are generally used to keep the data or the addresses of the next line from where a jump was taken place. Okay, or whenever we use a loop or branch instructions, the next address data of, or the next address as well as some important data are stored in the stack. I have discussed stack in very detailed manner in one of my previous lectures. Okay, so stacks are generally used whenever you are using functions, jumping the program from one end to another end or one function to another function, when we are using interrupts, and when sometimes we are using RTOS. So we are not going to talk about RTOS in this course. This is an advanced topic. But generally, stacks are used in these three conditions. A stack is a section of memory. Okay. And that was also discussed while we were discussing about the memory layout of ARM Cortex M4, where the stacks are actually allowed, or which region of memory is allowed for the stack. Functions are basically used, okay, are used by the programmer to avoid repetition of code. Okay, so now you remember that whenever you are looking at any program where you have to repeat the code again and again, then rather avoid repeating that code and use functions. Functions will help you to make a better or more readable code and avoid repeating the same code for multiple times. Okay, let us see why and how. So remember, whenever you are talking about functions, do remember about this word dry, or you can say do not repeat yourself. So a good programmer will try to avoid repeating the same code again and again. For that, he will use functions. Okay, this is discussed. So functions in general are also known as subroutine. So you have used this particular word a lot of time or many times in 8085. subroutine, writing a subroutine, jumping from one location to another location using subroutine and all. So subroutine is another name of function. Apart from that, some people or some books use procedures, and some books also refer functions as subprogram, or in many other languages they use procedure or subprogram, but all are same functions. So if you understand the concept of subroutine from 8085, the function is the same. In another language you may call it procedure, or in some other language you may call it subprogram. So functions are same. Okay. In general, what are the ingredients of a function? Every function should have its own name. Okay, function should have its own name. It should have its own argument. Most of the time, you may call it parameters also. Okay, parameters or arguments. And then the return type. The return type, when we say the type of data it is returning, sometimes integer, sometimes floating, sometimes character. So return type. Okay, so the data type which it is returning and the value which is returning, or sometimes it may not return anything also. So void kind of functions. Okay, so these three terms or these three ingredients are very important for any particular function. Let us check functions. Okay, first of all, we must understand few things about a function. That is, first is how to call a function. That means how to jump from one location to another location, or one program code to another program code. That means how to call a function. Then, of course, the type of returns which the function can throw. Okay, when the function is complete, what kind of data the function can throw out. Third, the naming protocol, or the way to name any function. And then the arguments which are passed in the function. Let us try to understand functions using code block first. Okay, so I'm not going to use this code. This is very simple, trivial code. Okay, this particular function. So suppose you are going to write a program, okay, where you just want to make, wait a second, I will comment this part. Okay, I will comment this part also. Okay, so suppose you are interested in printing a function or printing something on the, no, not running, working. Okay, printing just hello world. So you know that you can print this particular line using print function. Okay, slash n, done. But now this should be inside the code, I think. Let me check. Double quotes. Okay, but suppose you want to print this particular line 5 times. Some people or some programmers may use this particular approach. Okay, and what you are doing, you are printing the same line 5 times. Rather, if we follow the rule of good coding, do not repeat yourself. So we should not repeat the same code again and again. For that, what we can do, like I said, we can take the help of functions. Okay, so rather repeating the same code 5 times or 10 times or 20 times, what you can do, remove this particular lines, extra lines, because they are doing the same thing. What you need to do is you need to take the help of functions. Okay, so I will just uncomment this. Sorry, Control Z. Now what you are doing, you are introducing an integer, okay, I, and you are saying that I should be repeated 5 times or less than equal to 5 times, and keep on incrementing the I. Now this is the way to call a function. So you are calling a function with the function name. So the name of the function is print message. You can call it any name, okay. So it is your choice to give a name to the function. So everything that is in the curly braces, okay, or every term which is actually followed by this brackets, okay, are called functions. For example, let us check here which are there other functions in this particular program. So first of all, void print message, this is a function, you know that. Why? Because you have brackets, okay, and void here inside that, this is called the argument, which is with the elements inside the bracket are called arguments. There can be one, two, or many arguments for any particular function. And then, for example, print message is one function, print f is another function, main is one function, for is a function, and print message here again is a function. So one, two, three, four functions are there in this particular program. What we are doing, for every time the I is increasing from 1 to 5, we are calling this function print message. So the main program will start running in or it will just declare the integer I. Then it will call print message. The program will jump from here, okay, to here, and then print the message, and then it will return to the next line. And in this way, the for loop will keep on repeating until unless the condition is matched, that is, it tries to cross the value of 5. Up to that, the loop will keep on repeating. So you will be able to generate printf programming is fun 5 times, okay. So if you take this program and if you run it on your code block, you may generate programming is fun 5 times in the console, okay. So this is how you can use functions to avoid repetitions. Now let us check how we can use function and what are the things that we should keep in mind when we are going to use functions in embedded C or when we are programming our microcontroller. Few things that we have to keep an eye other than the things that we have discussed previously. Okay, now whenever you are going to use any function, okay, preferably use require prototype or do use prototypes in the C program. This was again introduced during C99 version of the C programming, okay. So C99 introduced this concept also, that you should always use prototypes of any particular function whenever you are writing a C program. We will come to that, how to use a prototype and all. For that, you can just go to, for example, in the IAR, you can go to right click, options, C++ compiler. And here you can see there is one button called require prototypes. Okay. Until unless you have checked it, there is no need to keep a prototype of the function. Okay. Otherwise, if this particular button is checked, you will start getting an error if there is no prototype declared for any particular function. So whichever function you use, you should always, if this particular button is checked, then in that case you have to declare the prototype beforehand, or you have to declare the prototypes before using the function itself. So you have to check this particular thing. So because this is introduced by C99 and this is the standard way of writing a C program. If you uncheck it, you don't have to specify the prototype, but it is always suggested, or it is always recommended to use prototypes when you are using functions. So check this particular button. From here onwards, whenever you are writing a program, prefer to check this button also. And then, okay, done. This is the first thing to remember, that you have to check the require prototype button when you are using functions in C programming. Second, let us check where we are repeating the same code. Okay, so let us in the delay function, if you see here in the delay function, okay, wait, I have not, yeah, so this is our code which is getting repeated, this part and this part. Okay, so what we can do is we can remove this while function and just use a delay function instead of writing this whole code again and again. Okay, so for declaring a function delay, okay, first of all we have to write the prototype for that. Okay, and how to declare a prototype? It is the same way that you declare a function. Only thing is prototypes are followed by semicolon. That's all. The same way to declare any function, you just declare the function and put a semicolon after that, and that will declare the prototype of the function. When defining a function with no arguments, please use void. Okay, for example, void, the name of the function is delay, and void, that means there are no arguments for this particular function. Rather, using this kind of approach, void delay empty bracket, so this is not a valid function. Okay, so if you are not returning any any return type is not there, then in that case, if you are using void functions, use void word inside the argument section. Okay, don't use or don't leave it empty. This is invalid, this is valid. So some of the rules which are there for the functions. Let us check how we can use the function to write a more simpler and more uh, legit code. Okay, okay, so we are using the same program which was there in this in the last example. Okay, now here this particular line, void delay void semicolon, this is defining the prototype. And remember, if you uncheck this particular C++, if you uncheck it, you don't have to declare the prototype. So I can just comment this section and then rebuild. Let us check. You can see zero error, zero warning. Okay, but if you just check this particular line, C++ code compiler and this particular require prototype, and okay, now if I just try to rebuild the program, I will get one error. If I go through the error, you can see here error at line number this one, PA045, function delay has no prototype. Okay, so because you are declaring a function and there is no prototype. Why? Because here you have opted for the option require prototype, and for a good programmer, C programmer, he should always follow this particular prototype. Okay, so require prototype, and then to declare prototype, you just have to use the same way the program the function is written, and then end up with a semicolon. That's all. That is declaring the prototype. Done. And we'll be using this kind of techniques, and if and I can show you in the header files also, they use this kind of techniques. Then after that, what we are doing, instead of repeating the same function again and again, we are using this particular line here, delay. That's all. Right, so whenever the program, after making the LED red LED high, delay function will be called. Delay function will jump from here to top here. Okay. And what is there inside the delay? Again, we are using int volatile variable counter. We are initializing the counter by 0 and making the counter keep on counting until unless it becomes 10 to the power 6. Then after the count is completed, this function will come back to the next line, which is here. Make the LED low, red LED low, and again call the function delay. From here it will jump to again this particular delay function, and it will again use the same delay function, repeat the same delay function. This is a better approach to write a function. Okay, so in this way you are actually making a more legit or more readable code. So run this code, rebuild. Okay, and you can run this code. So please make note of this particular technique, that whenever you are repeating the same code again and again multiple times, rather avoid that technique and just use a function and call that function whenever it is needed. That will make your program small, it will make it short, it will make it more legit. Okay, done. Any doubt in this part, how to use function, or what are we
No,
doing in
sir.
the function? Remember, use prototypes. If you want to become a good programmer, okay, use prototypes. And prototype is nothing but the same way that you declare your function, just use a semicolon after that, and this has declared the function. So this is prototyping. Then after that, rather than repeating the same code and again and again, you can use one time declaration of the function, and wherever you need, call that function from your program. Done. So this makes it a better or a more legit code. Okay, next. Okay, optimization low. Why we are calling it for optimization low? You can keep the optimization high. Okay, but when you are keeping the optimization high, we have to sometimes be very careful about those variables which do not have volatile with them. Okay, but otherwise if you are using volatile keyword, okay, you can use high optimization also. No worry about the optimization level. Okay, don't worry about that. Okay, done. Done. Mm, this is done. Okay, let us try to just clarify one thing. Let me just connect this board and load the program onto the board, and just for small clarification. Okay, I will take this particular program options, require prototype, debugger, ti stellaris. So now I'm going to load this program onto my board. I'm loading it, and okay, I will close the disassembly window because I know this program is correct. So I can see the blue LED always on and the red LED is blinking on and off, on and off, on and off, because here you can see the blue LED is on always, and the red LED inside the while loop is becoming high, low, high, low, high, low. Okay, this is done. Now, but whenever I pause the program, okay, I'm always in the counter. Okay, again I start the program and pause it. Again I am in this particular pointer or in the counter, pause the win. So any guess why always the program, whenever I am pausing, it is reaching to a counter only? Any reason for that? Whenever I pause, you can see I am in the counter section. Okay, if I stop this program, for example, I stop this program, I go to the next program where we were using the delay prototype. Okay, I'll take this code and upload the program. Any guess why we are always ending in the counter? Okay, I will upload this program. Done. Uh-oh. Okay, so the program is running, and whenever I pause, you see I am always in the counter section. Again, I continue the program. Stop. You are in the counter. Run. Stop. Counter. Run. Stop. Counter. So, any guess why it is always in this particular line?
So because majority of the times it is in the counter only and the other steps take very less time.
Yeah, these particular lines are going to take some nanoseconds. Okay, so in this whole section will take some nanoseconds, and this particular time is taking some hundreds or thousands of millisecond. Okay, so the probability of reaching here is more compared to this particular lines. Okay, done. That is done. Close. Okay. Okay, how the stack, and what are the things that we should keep in mind when we are using stack? Stack holds the local variables. Whenever we are using a function, before jumping to a function, the data, some of the data and the address of the next line will be stored in the stack. Okay, so the local variables, okay, and the return address, or where we have to come back, these two things are stored in the stack. And in the one of the previous lectures, I have defined almost everything about the stack, that the temporary registers R0 to R5, and then you have the program counter, link register. All these things are generally stored in the stack, and then the program goes to the function or the interrupt. So whenever we function is defined, okay, we have to keep an eye on the stack, because stack is going to take care of all the variables and the return address. Okay.
So,
Mm-hmm.
sir, if in any function we are defining a equal to 5, and then in the next line we're defining a equal to 4,
Mm.
then after that can we recover back the value when it was a equal to 5 because it
Yes,
says
yes,
that.
yes, yes. Local and global variables are, whichever variables are declared within a function are local variables. Okay.
So
So
previous value is we can access the previous value again.
yeah,
How
we can. If
how
we
do we
are
do
writing a function, for example, let us go to this. Wait a second. Back. Okay. So for example, here this counter is local variable. Okay. Why? The void delay, okay, is using this particular counter equal to 0. So this counter is local to delay function here. Okay, so this counter will be different from any counter which is declared somewhere here inside this main function. Okay, you can declare a counter somewhere here also, counter equal to 25. Okay, int counter equal 25. So this counter variable is local to main window. Here this counter is local to delay function. So these two will not be messed up. Okay, so if you need, I can write a program in the next class, and I can show you how same variables are managed or maintained when you are using local and global variables. And this is local to main, this is local to delay. Apart from that, I can use int counter equal to 35. Now this is a global variable. Okay, so global variables and local variables. Local variables, you might have studied about this. Local variables are only restricted to that particular function. They cannot be taken outside that function, or that those values cannot be taken outside that function. And here
Yes,
global,
but my question was different.
what happened?
If only we are seeing in the void delay only, and the value of counter is changing at every iteration of the while loop.
Hmm.
So all those values of counter are stored in a stack. So for example, first it was 0, 1, 2, 3. So all these are getting stored into a
No,
stack.
no, 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 no. No, why all the values will be stored in the stack?
So that's what that definition
No,
said.
no, 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 no. That's not the thing I'm saying. I am saying whenever you are jumping from one function to another function. For example, when you are going from this code to this code, so now you are coming out of the main function or while function. Okay, so when you are jumping out of this function, you will be keeping all the, I will show you, don't worry. Okay, so all the details which are required, for example, after the completion of delay function, you will have to come back to this line, right? And who will tell the address of this line? This will be taken from the stack, because before going to this delay, okay, you will have to store the address of the next line after the delay and all, and that will be, and some temporary registers data, that all those data will be stored in the stack. And when I was talking about the stack, I had showed some programs also how the stack is actually managing all the stuffs. Okay, so whenever you are jumping from this location to this location, okay, all the data required to come back to this line, okay, to this line, will be stored in the stack. Okay, and the status of, for example, the data register, this is also important. What was the previous status of the data register? That has also to be stored in the stack. Otherwise, when it returns from this delay to this line, how it will know that whether the previous LED was on or off? Okay, so this we can see from the stack also. Don't worry, we will see that. Okay, not to all. Let me go to the program and check how can we use arguments when we are writing the functions. So the previous function we were having delay, and in that delay we were using void. Okay, so the delay was like this. Delay was like this. Okay, so it was a void function. Okay, whereas in this delay we can pass the argument. This argument will be taken, and that argument can be used as a variable in the function. For example, delay, and then we are passing the argument 10 to the power 6. So when we jump from this position to this position, okay, now the delay takes an argument int iteration. And where is this value basically? Int iteration is coming from this value 10 to the power 6. Okay, so you can just, instead of writing 10 to the power 6 again and again in the delay, you can use the iteration variable, and then you can just go and change the counter value 10,000 instead of 10,000 or 10 million or 1 million. You can just change it to iteration, and the counter will keep on changing. So this is how you can use the arguments. And again, remember, now the whole functions declaration is void delay, in the bracket you have the argument. So the prototype, you will have to copy this whole line, okay, and copy paste it here, and then put a semicolon. This is your prototype. So prototype should be the same replica of the function itself. So now what else we have modified? You are using the same delay function, you are using an argument, and that argument you can keep changing. So you don't have to depend on the same delay, because in the previous example you saw that delay was same, but whereas now you can change the delay by just changing the argument's value. So delay, then argument, this argument will be passed here, and then you can change the iteration according to your choice. Okay, so you don't have to always have the same delay for making it on and off. So now here the program says the LED will be on for 10 to the power 6 times. Okay, and whereas it will be off for 5 into 10 to the power 5 counts. Okay, so now the LED will be on for a longer period, and it will be off for just half period of that particular delay which was called previously. So in this way, passing argument can help you to further improve the quality of the functions that you write. Any doubt in this part? Anyone having any doubt in this part? How we are using a function, passing the argument, and using that argument to further improve the way of writing our program. Any doubt in this part? Remember that prototype should be the same replica of the main function that you are using. Okay, so void delay int iteration, if it is this is your function, then add a semicolon to that, that is the prototype. Okay, done. Any doubt from this particular line? We are keeping the same code, we are just changing it bit by bit. Any doubt in this part? If not, then now let us see one more feature. In the previous program, we were keeping the delay, okay, within the program. What you can do is you can make one function and keep it as a file, and whenever you want to use that particular function, you can just call that particular file, just like our header files. For example, we have the header file tm4c gxl.h. Okay, here is our header file, and we are using this particular header file. Similarly, can we make our own file for delay, and that can be used wherever you want to use that particular file? For that, you just need to have two files with you. One is the .c file, okay. The other one is the .h file. So what is the benefit of using this .c and .h file? First thing, in this, what you are doing, you are just including the .h file, and whenever you want to use that particular delay function, you can use it here. For example, you are calling the delay function here, but if you check in the main program or in the program, there is no delay function. You can check here, there is no function for the delay. So where is this delay coming from? This delay is coming from the header file or the C file and the header files combination. So now first of all, how to make an header file? Now we are going to learn how to make our own header file for any particular function, or maybe you can keep them in some folder wherever you want delay or any other such rotation based functions, sorting based algorithms, and so on. You can create your own header files and use them wherever you want to use them in any main program. Okay, you remember that this part, okay, this part is the same that we have used in the program. Void delay bracket int iteration, and then int volatile counter equal to 0, and this part is the same that we have used in the previous file. So what you are doing here is, okay, you are taking any notepad, okay, in the notepad and just copy that particular file or the function, control C and control V. So this is my code which I want to repeatedly use in different functions or different programs. Okay, so this is my program. Now to use this program, I need to just create one more file, that is my header file. So first of all, let me save it. So save as, and I will create one folder in my head desktop. Right click, new folder. I can say delay header and C files. Okay, I just keep that in that particular folder, and I will give it a name delay.c. So this is my C file. Now in this C file, I have to include a header name also, so that whenever I want to use this particular function in any main program, I will have to just call the header file. Okay, so for that I will have to create one more file, which is the header file. So from the previous example, when we are discussing about the header file for the main program that was given by the company, okay, TM4C123GXL.h, we noticed few basic approach to define or declare any header file. What was the function, the main functions that we were using? If not define, define that file. Okay, so these two lines are there, so I will just copy these two lines, and in the header file I will just copy paste it here. So if not define, so if is there, so definitely we will have to have and if also. So and if, so these two, this section is what we need to write our header file. So what is the header file we are going to declare? We are not going to declare TM4C123GXL here, because this is there in the companies has provided it. We are creating our own header file and we want to give it a name. The name should be delay.h. Okay, so for that we can use underscore underscore. Remember, this is underscore underscore 2 times, and then remove this part and declare delay dot. Instead of dot, we will use single underscore. Okay, delay dot h underscore underscore. Okay, so if not defined, if delay dot h is not defined, then declare. Whom to declare? You have to declare the delay dot h. That's all. If it is not defined, define it. Okay, done. And what to define here? What to define here inside this particular thing? Inside this, we have to declare the prototype of the function that we want to use. And we know the prototype was nothing but you use the same way. This is the function name. Copy this. Okay, paste it here. And what is the difference between the prototype and the main function? Prototype and main function will have a just semicolon missing in the main function, whereas in the prototype you have the semicolon. So now this is my header file, so I will save it as a header file. So save as. Okay, so delay.h. Done. So this is my header file and this is my main function. Okay, but now in the function we have not called the header file. For that we will have to use just hash include, okay, double quotes, delay.h. That's all. Done. So we have the main file, which main function, which is to be used as a header file. That function is there. Done. We created a header file by using this particular macros. If not defined, define the header. Okay, then pass the prototype and end if. So this is the header file's declaration. And then in the main .c file include the header file. That's all. And whenever we want to use these two files, we can copy these two files from the folder wherever we have created them. So for example, here we have created delay header. I just copy these two files, Control C, and whichever project I am trying to work with. Okay, suppose I am working in this project, LNMIT. So ESD course related. I'm finishing this lecture, don't worry. Okay, IAR file. Assume I want to use those header files here. I'll just paste them here. Then I'll go to the main project and here I will right click, add files, and I will add the header file .h. That's all. And here I can use hash include double quotes delay.h. Done. And now I can use the delay function anywhere I want to use them. I can just remove this part and I can use delay here. That's all. And I can pass the argument. Okay, that's all. Done. Clear. So this is how we declare our own, or we can create our own header file and use them wherever we need to. Okay, I will close this project. No. And where we are using this. Yeah, done. This is all about creating our own header file, declaring our own header file, and using it wherever it is needed. Only thing you need to do is right click, add files, and use that particular header file. Okay, done. So now you have learned how to make your own header files also. With this, I am ending this lecture. And from functions, we learned how to make our own header files. Okay, thank you.